Alrighty, howdy folks. So let's get busy and get into chapter 2. So let's start with chapter 2, section 1, which is first order differential equations and just the preliminary theory. It's just got 2 slides in it. Maybe I should go ahead and introduce you to this. Okay, here is the idea in this section, folks. Up until now, rather in 1.1, what did we do? We were given a differential equation and also a solution. And the only thing that we needed to do was see whether or not that solution is actually a solution, that function is actually a solution of the differential equation. Nobody said to us, hey, solve this differential equation. Right? But now we actually are about to get into solving differential equations. And what mathematicians have found is a good way of teaching how to solve differential equations is to classify differential equations into first order and higher order differential equations. And just learn to deal with how to solve first order differential equations first, and then the second, third, fourth, fifth, all of them, they can be lumped into what's called higher order differential equations. And once you learn the procedure for, say, second order differential equations, the same procedure can be applied for the remaining ones. So that's the idea. Okay? All right. Without much further ado, the whole chapter 2, by the way, is all about first order differential equations, different techniques you are going to learn. And for that, I need to do define what's called an initial value problem. What is it? A first order initial value problem, IVP, is a differential equation of the form dy dx equals f of xy, and it is subject to the condition y of x sub 0 is equal to y sub 0. Okay, what in the world is this? It's just, hey, I have a first order IVP. I see. So that means you have a first order differential equation. Yep, I do. And you also have an initial condition. Yep, I do. That's what an IVP, first order IVP is. Now, let's see. Would you agree that dy dx is equal to f of xy? That is a first order differential equation? Yeah, you have a first order derivative, that's the highest derivative, and this is equal to some f of xy. So what's a differential equation? It's a differential equation it's an equation with derivatives. That's exactly what we have. For instance, you could have a differential equation of the form dy dx is equal to x sine y. Right? So that's a first order differential equation. And what's up with this y of x sub 0 equals y sub 0? That is an initial condition. What does it mean? It means when x takes on the value of x sub 0, y will have a value of y sub 0 at that time. Okay? For example, I could say y of 1 is equal to 2. That means when x is equal to 1, y is equal to 2. Or I could have something like t, uppercase T of 0 is equal to 100. Let's say uppercase T represents temperature. And 0, temperature is now a function of time, let us say. So t of 0 equals 100 means at time t equal to 0, the temperature of whatever you're looking at happens to be 100 degrees, whatever unit, Fahrenheit. Okay? So that's what a first order initial value problem is. And then there is a theorem called existence of a unique solution. And it's a simple definition. Let R be a rectangle in the xy plane defined by a less than or equal to x less than or equal to b, c less than or equal to y less than or equal to d that contains the point x sub 0, y sub 0 in its interior if f of xy and partial f with respect to y blah blah blah. Right? So what is this theorem about? Number one, it's about existence. Existence of what? Of a solution. What it is saying is, if you have an IVP, initial value problem, first order IVP like this, you are guaranteed of the existence of a solution, meaning there will exist a solution to that kind of an initial value problem. Guaranteed. Provided certain conditions are satisfied, of course. And also, that solution that you find will be unique. Meaning, once you find a solution, that is the solution. You don't need to find some other solutions. Okay? And there won't be other solutions. What's so big deal about that? Well, the big deal is, suppose uniqueness is not guaranteed, and I find a solution to one of my problems. I find a solution. Let's say that's not the only solution. And in fact, that's the solution that doesn't apply to this. Even though in my situation, that's not the best solution. There is another solution apparently, which probably is better. So that defeats the purpose. So mathematicians would love to have unique solutions. Not only mathematicians, physicists and all that. For example, let's say you're talking about a spring attack, a simple pendulum. Okay, that's even better. Can you imagine a pendulum swinging back and forth? Let's say you try to solve. You basically, in a case like that, you're trying to figure out what would be the position of the pendulum at different times. What's the position, angular position of the pendulum as a function of time? And if one solution says cosine t and the other solution says sine t, which one is right? At t equal to 0, is the value sine 0, which is 0, or is it cosine 0, which is equal to 1? Is the pendulum located at 1 radian, or is it located at 0 radians? What is the position? See, now there is that ambiguity because you don't have a unique solution. Cool? All right. Now let's look at this. All the first part of it is saying, let's R be a rectangle in the xy plane. That's a simple thing, right? And it's bounded by a and b and the x direction. X is going from a to b. In the sense, horizontally, you have this interval of a to b. And vertically, you have an interval of c to d. Those are the boundaries of this rectangle. Okay? Let R be a rectangle in that xy plane with those dimensions. Now, this point x sub 0, y sub 0, where did they come from? They came from that initial condition. X is equal to x sub 0 and y equals y sub 0. Let's say that point x sub 0, y sub 0 is inside of this rectangle. Alright? And if f of xy, which is this right-hand side of the differential equation, and also partial f with respect to y are continuous on this rectangle. Okay, that means there are no jump discontinuities or infinite discontinuities, things like that, or removable discontinuities. Then you are guaranteed that there exists an interval I centered at x sub 0 and a unique function y of x defined on I satisfying the initial value problem. So surrounding that x sub 0, there is an interval over which you are guaranteed to find a solution. That I may very well be your A to B, that interval A to B. But it could be a subset of that interval. Okay? Now, I got good news. I saved a bunch of money on my car insurance by switching to Geico. No, I'm just joking. The good news is, if you didn't understand this, don't worry too much about it. Okay? Let's move on. Now, with that, let's go to this main section, section 2.1. Now we are getting into business. This is solving first order ordinary differential equations by one particular technique. Like I said, I don't know if you had a chance to recall this one or remember this one. The entire chapter 2 that we're going to deal with is learning different techniques to solve first order differential equations. Okay, now the first thing that we will be exposed to is this separation of variables technique. All right, let's see what in the world it is. A first order ODE of the form dy dx equals f of x over g of y can be solved by the method of separation of variables. The moment you multiply both sides by dx and also by g of y, you can isolate the y terms and the x terms. You can have all the y terms on the left hand side in the form of g of y dy, and all the x terms on the other side, for instance f of x dx. And once you isolate like that, you can just integrate. Right? You don't need any complicated integration. We're just talking about the kind of integration that we learned in Calculus 2. What do you mean by Calculus 2 integration? Yeah, there is some kind of an integration that you learn in Calculus 3, which is slightly different. What? Yeah, don't worry about it. Okay, that's also pretty easy, and we'll learn about it. So here, you just separate like this and you're done. I'm going to illustrate this with a whole bunch of examples. All right? So don't worry too much about if you didn't understand what this f of x, what did you do, man? Okay. Here we go. Is this a first order differential equation? Yep. Can we solve this by separation of variables? Yep. Why? Well, the question is, can you separate all the y terms onto one side and the x terms onto the other side? Yeah, right? Can we divide both sides by x plus 1? So we'll be left with dy dx equals x plus 6 over x plus 1. Can we multiply both sides by dx after that? Yep, when we do, aren't we going to be left with dy on the left hand side and this stuff on the right hand side? And now, let's just go ahead and integrate both sides. As simple as that. So, if you know how to integrate, you're done. So, let's see. How do you integrate x plus 6 over x plus 1? Please do not give me a heart attack by saying, hey, I can cancel the x and x, man. No. You cannot. Right? So one way is you can do long division. Divide x plus 6 by x plus 1 and figure out what the quotient is and what the remainder is. Okay? Or better yet, if you look at my videos on integration techniques, where I used partial fraction decomposition, if you see that section, boy, this piece of cake, this is nothing. Okay? All right. So this is sort of a clever method. If you can be a bit clever, it would come in very handy. And that's what I'm going to show you. Check this out. Can I write x plus 6 as x plus 1 plus 5? Yeah, after all, 1 plus 5 is 6, so we get back x plus 6. But why did I split this as x plus 1 plus 5? That's because in the denominator, I saw an x plus 1. I said, hey, can I get an x plus 1 on the top? Yeah, go ahead and write x plus 1. But, well, of course, you need to add a 5. Otherwise, this numerator is not equal to that numerator. So x plus 1 plus 5. Now, are we allowed to say this is equal to x plus 1 over x plus 1 plus 5 over x plus 1? Can we separate the fractions? Yep, we can. So that's what I'm going to do. And x plus 1 over x plus 1 is just 1. And we have plus 5 over x plus 1. Is the integral of a sum equal to sum of the integrals? Yes, it is. What's integral of 1 equal to? X. What's integral of 1 over x plus 1? Natural log of absolute value of x plus 1. Cool. X plus 5 times natural log of absolute value of x plus 1 plus c. Right? We always have to say plus c. I just mentioned it casually. Yes, you really have to say plus c. I know you must have hated your math teachers because, you know, your math teachers didn't gave you a hard time or took off a big chunk of points because you didn't put the damn constant there, right? Guess what? Nothing has changed. Okay, let me pause here. I forgot to get my writing pen here. Good. Sorry about that. I'm back. Let's see. I gotta do that, and I gotta do this. Cool. So where was I? I was saying, yeah, you must put a constant. Now, sometimes what happens is, or maybe I'll express it this way. Is it okay, instead of plus c, I could say plus natural log of c? Would that be okay? Yeah, if c is a constant, arbitrary constant, natural log of c is an equally arbitrary constant. Why do I say that? Because it's entirely possible that sometimes you get a certain answer the way you do, and the book will have the answer stated in a completely different way. And you'll be like, what? I got the wrong answer. Maybe not. Let me illustrate that with a simple example. Let's say the answer that you got was natural log of y is equal to natural log of x plus c. Cool. Now if you look at the book, at the end of the book, you will see that the answer is actually y equals cx. Answer is what? Y equals cx. And you're like, what in the world is that, man? Where did that come from? Well, what they've done is, they said, I'm not going to take the constant to be just c. Instead, I'm going to call it as natural log of c. And then recognize that this is natural log of c times x, x times c, or c times x. Now, natural log of y is equal to natural log of cx must imply y is equal to cx. Right? So the answer that you got of natural log of y equals natural log of x plus c, was that wrong? No. That's perfectly valid. So far as I'm concerned, in a test or quiz, you leave the answer as natural log of y equals natural log of x plus c, I'll give you full credit. Cool? I will give you full credit if you don't simplify, especially in that particular way. All right. So the point I'm trying to make is, yes, you can, in fact, you must have the integration constant, but it doesn't have to be plus c. It could be, any arbitrary constant. Can I tell you a quick story about that one? Well, when I was teaching Cal 2 a few years ago, I told my students, hey, you can actually, you don't have to say a plus c, You can say natural log of c or e to the c, sine c, ha 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 ha. And so a quiz came up and about integration, and I was grading, and all of a sudden I see that this particular student had worked the problem out completely and everything was fine, except I saw that he had a plus e to the sine of natural log of cosine c or something like that. And I was like, what? Where did this come from? And then it hit me. Oh, okay. And I looked at the front page to see who it is, and I saw the name of the student, and okay, that guy, yeah, all right. And so I asked him in class, why do you do that, man? And he gave the most profound answer I've ever heard in my life. He shrugged his shoulders and went, Now, how much more profound can an answer get than right? All right, let's move on. So y equals x plus 5 natural log of, so what? Did I do this right? Like when I said, so y equals x plus 5 natural log of, what happened to the absolute? I hate absolute values, man, so I just took it out. No, you cannot do that. But here is the idea. Please pay attention. Whoa. See, when we have absolute value around x plus 1, the thing about it is, x can be anything except negative 1. What? X can be any number except negative 1. If we have absolute value. Really? Could we? I thought natural log was not defined when for negative numbers. Yes, you're right. Could we have negative 10 for x? Yeah, what would happen? Negative 10 plus 1 is negative 9. Absolute value of that is positive 9. Natural log of positive 9, of course, is a fine, perfectly defined number. Right? So, what it is at x equals negative 1, natural log is not defined because natural log of 0 is undefined. So that means there is a discontinuity to this function natural log of absolute value of x plus 1 at x equals negative 1. So what? So what is the problem with that is, that means this differential equation, the function would be not differentiable at x equals negative 1. That is because there's a theorem in calculus 1 which says if f is differentiable at a, then f is continuous at a. But the contrapositive of that is, if f is discontinuous at a, then f is not differentiable at a. If f is not continuous at a, that is, then function is not differentiable at that point. So at x equals -1, there is a discontinuity. That means at x equals -1, this natural log of absolute value of x is not differentiable. When something is not differentiable, how can you claim it to be a solution of a differential equation? Right? So what we must do is say that this is a solution on either positive interval or the negative interval. So that point x equals -1 is separating things out, right? To on one side and to the other side. So you pick one side. What I did here is I just happened to pick the positive side. And that meant what positive side of what? For x greater than -1 is what I picked. When I pick x greater than -1, this quantity x plus 1 is going to be positive. That's what I mean by it. And absolute value of a positive quantity is just the quantity itself, and that's why I can get away with with a parenthesis around x plus 1. Did you get that? I picked x greater than -1, by which x plus 1 is guaranteed to be greater than 0, and that means absolute value of x plus 1 will be simply x plus 1 by virtue of x plus 1 being greater than 0. And so I can remove the absolute and just use a regular parenthesis. But I have to say that x is greater than -1. This solution applies only in that situation. Okay. Now, or alternatively, if you were to be the kind of a rebel and say, no man, I want to pick x less than -1. Okay, be my guest. But then be sure to replace absolute value of x plus 1 with a negative of the quantity x plus 1, which is -x minus 1. Okay. Allow me to make one more very important point here, please. Well, which one should we take? Why should we care about? What does this depend on? As to which solution we actually pick? Check this out. It all depends on the initial condition. Can you guess as to why it depends on the initial condition? Whether we pick this top solution or the bottom solution? Okay. Suppose the initial condition is y of 3 is equal to 5. In a situation like that, could we pick the bottom one? No, the bottom solution applies when x is less than -1. We have x to be greater than -1. X is 3 in this case, right? X sub 0, which is an x, is 3. So we cannot pick the bottom one in a situation. We must pick the top one, which applies whenever x is greater than -1, and our initial value of x happens to be 3. Cool. On the other hand, if the initial condition was y of -4 is equal to 2, then we must pick the bottom one. Cool? That's the idea. All right, let's move on. Solve this differential equation. One thing is, because all these problems are in section of separation of variables, what technique should I apply, man? Obviously, separation of variables. The question is, can we really separate the x's and y's in this case? How? Please pause the video and see if you can come up with a way of separating the x's and y's. Okay? All right. Now, this is what we have. On the right-hand side, can I factor out a e to the -y? Factor out? What do you mean by factor up, and how can you do that? You don't... Wait a minute. Is this in the form of a to the m plus n? Is a to the m plus n equal to a to the m times a to the n? A to the m plus n, isn't that equal to a to the m times a to the n? Yep. So this is, the second term is actually e to the negative 2x times e to the negative y. Now of course we can easily factor out e to the negative y. That's what I did. Cool. And you get 1 plus e to the negative 2x. E to the negative y times 1 plus e to the negative 2x. And can we separate the x's and y's? Yep. Divide both sides by e to the negative y, or multiply both sides by e to the positive y. When you do, on the right hand side you won't have a y. E to the y times e to the negative y is e to the y minus y, which is e to the 0, which is 1. You with me? E to the y times e to the negative y is just 1. E to the y minus y, a to the m times a to the n is a to the m plus n. E to the y times e to the negative y is e to the y plus negative y, or y minus y, e to the y minus y, e to the 0, e to the 1, which is rather equal to 1. Okay, and also, can we divide both sides by e to the x, multiply both sides by dx? So all those manipulations I did. When I did, I ended up with integral y e to the y dy on the left hand side and this on the right hand side. Cool. The question is, do you know how to integrate y e to the y? Yep, that's just integration by parts, right? And when you do, you get y e to the y minus e to the y. And this one, how do we integrate the right hand side? Can I separate this into two fractions? 1 over e to the x plus e to the negative 2x over e to the x? Yeah. What is 1 over e to the x? E to the negative x. What is e to the negative 2x over e to the x? E to the negative 2x minus x, which is e to the negative 3x. So the left hand side is y e to the y minus e to the y. Do integration by parts and that's what you get. An integral of e to the negative x is negative e to the negative x, and e to the negative 3x integral is negative 1/3 e to the negative 3x. Thus arbitrary constant, the integration constant c. Cool? All right. Solve. What technique? Yeah, separation of variables. So what I did is I wrote this y plus 1 the quantity square over x the quantity square as y plus 1 the quantity square over x square, and then multiplied both sides by x square, giving me x square y natural log like this, and then separated the x's and y's. And the question is, and integrated both sides. And do we know how to integrate x square natural log of x? Well, again, integration by parts. You say u equals natural log of x and dv is x squared dx. If you watch my video on integration by parts, you will see something called ILATE. Logarithms are a good choice for u, not a good choice for dv. And algebraic one, x squared dx, is a good choice for dv. Okay, and du is 1 over x dx. V is, you need to integrate x squared dx to get v, and x cube over 3. And so uv minus integral v du is what you would have. Uv is natural log of x times x cube over 3, which is what I wrote as 1/3 x cube natural log of x, minus v du, minus 1/3 integral 1 over x cube dx. Cool. And that equals, well, how do we solve this one? The right hand side, the top, just FOIL that out. Or if you recall, the way I would typically do is I know the identity a plus b, the quantity square, is a square plus 2ab plus b square. So this becomes y square plus 2 times y times 1, which is 2y, plus 1 square or 1. And then we separate out into 3 fractions. Y square over y is y, 2y over y is 2, and 1 over y. Those are the 3 terms you see here. And those are simple to integrate, and you just do that. Cool. And here I'm supposed to say natural log of absolute value of y. If I happen to miss that, just ignore that. I like this one. dq dt equals k times q minus 70. There's nothing big deal about this one. Usually, yeah, by the way, usually I change everything into y's and x's. I don't see any reason why you have to go with the q's and t's and r's and all kinds of other variables. Just adds to confusion. However, there are some instances where I do want to leave it because of some practical significance to that equation. And this is actually a practically significant equation, and I'll talk about it in just a second. Okay, so here we will use the separation of variables technique, and then dq over q minus 70 equals integral k dt. I multiply both sides by dt divided by both sides by q minus 70, and that gives us this, and plus natural log of c. Ooh, look at me. I took the constant as natural log of c. Okay, with the idea that now I can raise both sides to the power of e. Is that a valid thing to do? Can you raise both sides of an equation to the power of e? That is okay. Okay, so when you do, e to the natural log of something is whatever that something is, and so we have q minus 70. And this is e to the kt plus e to the quantity kt plus natural log of c. That's what we have. Now, obviously, this is equal to c times e to the kt, right? What? Obviously, the right-hand side is equal to c times e to the kt. How'd you get that, man? Well, can I write this as e to the kt times e to the natural log of c? So, when I do that, do we recognize that e to the natural log of c is nothing but just c? That's the idea. Cool. So, what's the issue here? Q minus 70 is equal to c e to the kt. So that's the solution to this one. Or we can write this as q equals, that's what we are solving for, equals 70 plus c e to the kt. Okay, what's the big deal here? The big deal is, let's say q at 0 is 100. What? The value of q at 0, that means when t equals 0, the value of q is happens to be 100, let us say. Can you figure out the value of c now based on that? Yeah, plug t equal to 0. So when you plug t equal to 0, kt becomes 0, e to the 0 is 1, and so this whole thing reduces to c. c times 1 is c. Are you with me? C times e to the 0 is c times 1, which is c. And the q, we should replace that with a 100. So 100 equals 70 plus c, and so c equals 30. So in the event we have the initial value Q of 0 to be 100, then this equation is Q equals 70 plus 30 e to the kt. And usually this k is a negative number. And so here what I have shown you, the graph of, suppose k were to be -1. Then we have this equation. This is where Q of 0 is 100. At when t equal to 0, would you agree? This is a value of 100. The Q value is 100. And notice how the graph looks. Why do I care about this? I care about this because this is precisely what happens when you heat, say, a pan to 100 degrees and you leave it in a room with ambient temperature 70 degrees Fahrenheit. Then the temperature of that pan will start to decrease and reach what is called a steady state. And when it reaches steady state, it has a temperature of the room, which is 70 degrees. And it's an exponentially decreasing curve. Initially, the temperature drops fairly quickly, but it takes a fairly longer time to actually come to the room temperature, right? So that's the nature of this. This is Newton's law of cooling. So when you take heat transfer, some course like that, you will bump into this equation. Cool? All right. Maybe I'll pause and make this into a next video.